Well, welcome to this special episode of the Dental Guys at the Academy of Osseointegration 2024. I'm Wes, the Dental Guy.
And I'm Don, the Dental Guy. And, you know, we've enjoyed very much getting to speak to some names that some of which we've spoken to before, some of which we haven't, and get to really discuss some topics that have been largely focused on one thing, mainly so far, periimplantitis. But this is going to be a little different conversation.
Good evening, Astra.
That's right. I still remember. Good morning. Good evening. Good morning. We remember,
but it's evening.
Back to the days.
Right. It was morning before.
That's right. So we'd like to introduce, and for those of you who've been watching the show for a while, probably needs no introduction, but Dr. Michael Norton's here with us. Thank you for being here.
Thank you, guys. Pleasure. Appreciate the invitation.
We're excited to have you on the show.
Yeah. This has been, we've had some good conversations in the past. And, you know, one of the things that's kind of been the theme of our show this year, we've kind of had a theme that sort of developed of, you know, we talk a lot about what's messing with us. What are some things that are changing the way we think? And we'd like to maybe explore that a little bit more open-ended today with you. And we have some very specific things we want to talk about because, you know, reading some articles or some things out there that we think you would be interested in. But just so far with this meeting, tell us is there anything messing with you? Have you seen anything interesting, anything changing your mind or making you think about something completely differently? Or is it so far things you these are things I expected?
Well, I think there are a lot of things that one might have expected. I mean, in the opening session, I thought it was a great session on periimplantitis. You mentioned that that's been a theme for you. I think we heard some very predictable approaches to that from various quarters. And what's clear is that there's plenty of disagreement, and you know I love disagreement. So, but no, what it's done for me, I think, is I sit in those sessions and I actually challenge my own dogma, and I ask myself, you know, maybe I'm wrong. I have to say, in that particular session, it only reinforced my own dogma, but. Yeah, I mean, I think it's important that we have that debate, and if everybody's singing from the same song sheet, then we really don't need a conference, do we? So.
That's right.
Yeah, that's important. Well, one of the things that we've seen, as we do many times when we come to this meeting, is companies presenting new designs, new ideas, and we've seen some new implant designs, for instance, and you know, we kind of been thinking about, you know, there's some companies that have a lot of designs, a lot of different designs. And even in one company, you might see, you know, 8 or 10 different designs. And the question we have for you, Michael Norton, is how many designs do we really need?
Oh, yeah, that's a leading question.
Yeah, it is.
Well, I think it's clear that, you know, there's a difference between design for innovation and design for design's sake. And I do think that we are currently in a bit of a rut where many of the manufacturers are designing for design's sake without actually offering any necessarily innovative technology. And, you know, people ask me often about the pace of change of implant design, but you know, I placed actually the very world's first microtextured, microthreaded, platform switched, for want of a better term, internal conical implant in a patient in 1992. And if you walk around this exhibition hall, you'll find that most implants today are microtextured, microthreaded, conical interface, platform switch. So what's changed? I suppose maybe thread technology has changed a bit, but I can tell you that there is nothing really innovative in any of those thread technologies. They're all the same basic kind of thread. There are some very interesting thread technologies out there, by the way, in the orthopedic sector that haven't come into this field that are entirely different to what we see here today. So, I think I suppose it's a bit like the car business, isn't it? Every year they got to come out with a new design, but once in a blue moon, a car manufacturer will do something revolutionary, like introduce an airbag, right?
That's right.
And that is a true revolution, and then eventually every car in the world has an airbag.
Well, I like that he brings up the car analogy, because in the United States, the Ford F-150 has been the number one selling car/truck in the United States. More F-150s have been sold since its release years ago in the 60s. And if you look at the design characteristics of that car manufactured, it has really not changed except for just some plastics and metals, and maybe, we've changed the engine per se, but it is essentially the same thing. And it seems very daunting for new clinicians that are interested in starting to place dental implants, because you and I and John, we have the knowledge of what 1992 looked like.
Correct.
Now, it's not the 90s. It's not the 90s, and we could sit in a lecture to this morning and understand why it's not the 90s, and we know some of the things that you and I lucked out on when it comes with that micro-threaded, platform-switched implant that you've been placing for so many years. We did luck out a little bit, I feel like, by the way that implant was designed. But today, clinicians really that are new, how are they choosing a dental implant to place?
It's overwhelming.
It's overwhelming. And I'm confused about how to teach this and how to help someone and to help them get past some of the cool factor.
Yeah, I think one of the big problems, frankly, in that is that if every implant offers variations of the same features, then maybe there isn't anything to choose from. Then you're looking at things like brand recognition, service quality. Do you like the look of your local rep? Right?
I mean, honestly.
I mean, that's really sort of what it might boil down to. And, it's quite interesting. So obviously you've had me on here before talking about talk. I mean, that test story interview, I think, seems to have been quite a popular subject. And, even I'm starting to get a little bit tired and a little bit bored of the high talk versus low talk debate. It's gone on for so long, and you may or may not be aware, but I mean, I'm now looking to new ways, third ways, alternative ways.
Well, it just so happens that we might have that right in front of us now.
Okay.
So that's one of the, and I want to just for a moment hold on that, okay? Because I want to just kind of finish the thought process a bit on when we look at some of the, still where we do see this change, at least in design. It seems to be that people, and this does apply somewhat to the periimplantitis discussion, is roughness and what is the correct roughness and what is the, but we wonder if you could speak to the idea that we seem to see that, connections, it almost seems like there is maybe an inverse correlation between the quality of the connection and the more polished surfaces that we see. In other words, are we trying to account for what may be bone loss that's going to happen by saying, well, we need to create a surface that's cleansable because it's going to happen? Is there anything to that, or is this something that maybe we're just reading wrong?
Well, I mean, it's a very good question, and just to take a step back from that a second, you say, what can the young learn today? We've been around. The truth of the matter is that implant dentistry is an evolved science over the last certainly 30 to 40 years, if you separate out the original Brandemark epoch, for want of a better term. And the past informs a great deal about why we are where we are today. And so to your point, John, we've been through the so-called hybrid design implants in the past. And I can't help sit there listening to these lectures and looking at these slides and ask myself, have I missed a trick here? Because we already did this and we saw it didn't work. So why are we revisiting it? I mean, one thing that really struck me in this afternoon's session was the debate that was presented to us about the idea of using a tissue level design implant in a submerged bone level way. Hammerly published a study on that in 1996 and showed categorically that you always ultimately lost bone down to the rough surface. Now we're being told, look at these beautiful x-rays, we don't lose bone around this polished collar. So I'm kind of curious, what's changed about machine titanium today that wasn't true in 1996? I don't know what I'm missing here, but I'm missing something.
It's very frustrating because so many people have recency bias and they have a short-term memory of what, we really have already.
Well, we saw this with composite bonding, and I won't go down this rabbit hole too far, but one of our favorites, Harold Hyman, when we interviewed him we said, okay, so let's talk about the generations of adhesives, for instance.
Love it.
And he said it was just old wine in new bottles. It's the same idea, right? And in fact, it's gotten worse as we've gone up in generations. The fourth generation is still the gold standard, for instance, in bonding. But there's just this need to do something that seems...
So there's to my earlier point, John, that's exactly what we're seeing. Design for design's sake. It's reinventing the wheel because we aren't having an airbag moment in implant design, and they don't come along often. Okay, they really don't. Not in the car industry, not in our industry. They don't come along very often, but by God, are we desperately due for one.
We're ready.
Yes.
We're ready. But
so let's talk about the third way, or a different way to change the thought process. And we think you might be talking about bone glue, maybe. Are we on to something with that?
That's one possible third.
Okay. So we've been seeing some publications, right? And most recently, even Michael Picos published in IJPRD just last month, I believe, on a 3-year human follow-up.
The first
3-year follow-up on this, showing we've got the study up because we were talking about mineral or organic resorbable bone adhesive, MORBA, right? So we know you've been involved in some of the basic science with this as well as some of the development. So for the listeners who don't have any idea what we're talking about, because there will be many, what is that?
Okay, so let's take a step back and first of all put it into context. There's a million bone materials out here, okay? There's a million bone cements. Polymethyl methacrylate is a commonly used cement to fill in a void around a hip implant, for example. We all know this. Bone cements, whether it's PMMA or calcium sulfate or any other one of these, the vast majority of them are exactly what they say. They are cements or they are fillers. They don't possess an actual adhesive property like gluing bone together. Nobody's ever had their bones glued together when they break their leg. They have plates, they have screws. My son just broke his ankle in 3 places. He has plates and screws. So the mineral organic bone adhesives basically are a new category of material with no precedent to date. They're all derived. The ones that are currently being developed are all derived from the marine biology. We all know that mussels and sandcastle worms and all these animals stick tenaciously to the hulls of ships whilst they're submerged in water. If you take your finger and you put a bit of super glue on it and you stick it in a glass of water, it's not going to stick. And yet we all know super glue is an incredibly strong glue. But wet environments do rather interfere with adhesion. So what these people have done is they've worked out how these marine animals create an adhesive that works in a wet environment. And the mineral organic bone adhesives are truly adhesive. They are glues. I mean, when you stick 2 bits of bone together with this stuff, you can't break it. It's unbelievable. More importantly than that, though, they are osteopromotive. So we can't call them osteoinductive or even osteoconductive. They seem to have a different process. The way in which they stimulate bone formation, angiogenesis, and so on. And it all revolves around one amino acid called phosphoserine. And what we're starting to learn with phosphoserine is that it almost has as much potency as BMP2. I mean, it really has an impact on bone. So these glues are resorbable. They are replaced by bone. And it will be in the not very distant future, I am sure, that these products will become a commercial reality. And instead of getting plates and screws, people will be having their bones stuck together. And instead of osteoporotic elderly ladies having to have toxic exothermic methyl methacrylate pumped into their femurs to hold their hip implants in place, they will have glue. And that glue will actually convert to bone. And it's really a very exciting...
Now that sounds like an airbag moment.
It's definitely got the potential
yes.
to be an airbag moment.
I think primary stability is what a lot of implant innovators have tried to really... They've changed their thread design to try to get... So we can do something immediately or quicker, right? The whole goal was to give people teeth. Whether it be in 2 weeks when our crown gets back from the lab, or maybe.
But then we see these reports where you know we're seeing these studies, basically these case reports coming out of an implant with zero stability, zero ISQ or torque. We can inject potentially this material around them, and within 10 minutes, I believe, or something along those lines, we have complete stability.
I could, well, you'll see in the study, I mean, it's published this month in JOMI, you'll see the ISQ graphs, and the key bit of the graph actually is the first two readings, because they're taken 15 minutes apart, and you will typically take, I mean, we were using very unstable implants in the study, so these are implants with often less than 50 ISQ. And they'll go from 50 or 45, and 15 minutes later, they'll be 75.
Wow.
Right?
Unbelievable.
I mean,
that's unbelievable.
That on its own is kind of a proof of principle that you can manipulate stability a third way.
That in itself could change implant design.
Oh, yeah.
Oh, I mean, yeah, and we haven't even started with that, Wes. I mean, you know, maybe there'll be an implant design that gets the best out the glue.
That's right.
Right.
But we
so
haven't
we'll change that material.
We haven't even started
got
with
there.
it.
Well,
No,
maybe
no.
let's start with what we did see, which there were not everyone was a success.
No.
But the comment I believe that was made in this study was we learned a lot.
Yes.
About how to manage this and how to handle the material through this. So speak to that, since this was your investigation on what did you learn?
Well, I think, you know, for me, it was also a really fantastic experience. One of the problems in our field is, you know, implant dentistry is replete with research, right? I mean, there's so much research published, but actually when you look a lot of that research, it isn't sort of first in human clinical trial pharmacological type level research. The FDA have actually categorized these materials as being combination, so they're not medical devices, they're medical with pharmacological. So that, of course, puts the burden of scientific rigor on a much higher level playing field than we're used to having in dental implants, which are basically medical devices, and so the rigor is much lower. So for me to be involved in that kind of a first-in-human clinical trial was a first for me. And having to deal with the regulatory authorities on a product that is now a combination product and not just a medical device was a real eye-opener. So you have to read that study in that context. This is not just another medical device. This is something with potentially some kind of true sort of biological impact, like BMP.
Yes.
And there's a learning. It's a first-in-human clinical trial, and the problem is that the assumption that you can translate from the animal to the human, and we had the most incredible animal data, actually published by Dave Cochran,
Yes,
another one of our past presidents here. And, his research was mind-blowingly good. The histology was just, it took your breath away. And yet, when we took it into the human, we found it wasn't quite so straightforward. And there were 3 centers for the first-in-human clinical trials. You alluded to one, Mike Pecos here, and Dave Cochran's group was another, and mine in the UK. But my protocol was slightly different, because I felt that if you really wanted to really prove this product did something, you had to put a prosthesis on the implant straight away.
Of course you did.
Right?
Naturally.
Right? Does that surprise you?
Not in the least.
So, Pecos and Cochran's groups, they weren't immediately temporizing or loading their implants. And clearly the challenge was potentially a challenge too far, or maybe the material needed modification. Indeed, we came to that conclusion. The protocol that we established for use in humans was established based on what we'd done in the animal model, but actually we realized that there were some aspects to our protocol that were harming the glue itself, harming the bond between the glue and the implant. So we sought a request from the regulatory authority in the UK to remove those steps from the protocol. And as soon as we started to remove certain steps, and as soon as we started to have a better understanding of handling properties, of setting times, and so on and so forth, we suddenly saw a huge change. So in that study, the overall success rate, I think, was 71.5%. But actually, if you look at the success rate after amendment changes, the success rate was 87.5% success, just by learning.
Yeah.
Right? That's what a first-in-human clinical trial is all about.
Of course.
So I don't see a 71% success rate as a failure or something to be ashamed of. On the contrary, I think the study absolutely proved the potential for this material. And now we have to work on making it so that you can take an unstable implant and give that implant the same success rate as a stable implant, but without having to go through, aggressive threads, radial outward compression, bone fracture, and resorption, and all the rest of it.
I love Mark Ludlow's presentation today, and he was so vulnerable to show those things. And wouldn't it have been nice to have some of this bone glue
well,
in that situation?
You can let your mind sort of run wild with the possibilities. Like you say, I mean, you start to think about how this could affect many, many, many things. But I think, just as you said, just the iterative changes as you learn and you learn and you learn, we're just excited to see where this takes us, because, we're, as you say,
using BMP was interesting to me. The problem with BMP is the cost. We brought that to the chair side. I brought it to implement. You did too, with some of the surgeons we work with. It's incredible. I remember telling my dad, who's an engineer, I'm like, Dad, literally, we can grow bone just about on anything. And I showed him like some surgical pictures and then CTs afterwards, and he was like, this is incredible. I mean, he walked in and he told Mom, he was like, Wesley's growing bone. I was like, well, I'm not. Just this material is, but it's pretty special. BMP it's hard to use it because of the cost.
That was one reason, yeah. And so sometimes the idea of when you're dealing with biological and pharmacological type of materials, it's very different. And so I'm sure you're getting to be exposed to some new thought processes.
But I think also with BMP, it didn't always deliver in the human in the same way it did in the animal.
Exactly right,
studies.
because there were cases where we used it and we were like, that doesn't look That didn't look like
And for what you were spending, you wanted a better result than that.
Absolutely.
Yeah, right.
And hence, it left.
So what's the next step with that? What's the next step with that material?
Well, I think you have to look at the glue in a much wider context. Dental is really just a very, very tiny speck of a side. It's almost a bit of a digression from its true value, which is in fracture.
We
fixation.
talked about that. Can you imagine what it could do?
Yeah.
Oh, it's huge. I mean, it goes beyond what even you might imagine, because they've also done sort of proof of principle studies for things like vertebral fusion. So you can actually just squirt the stuff between vertebrae, and a year later it's one solid block of bone,
and not have to put cages in,
and not have to put cage. You can make a more aqueous form of the glue and potentially inject it into osteoporotic bone to increase the density of bone. NASA has taken the glue to the space station twice already, because they're so interested in the potential it might have for astronauts on their way to Mars or whatever, because you can inject it percutaneously to stabilize a fracture. An astronaut could do that themselves.
Think about X-tip, but with bone glue. I mean, seriously.
No, I mean, it's
unbelievable.
It is undoubtedly the most exciting thing I've ever been involved with, other than the launch of the Astrotech implant in 1990.
Well, we're not bored anymore.
Yeah, that's right. No, we've and so this is why one of the reasons we knew we'd be speaking about this, because when we saw that, we could just tell, like, this could be one of the biggest things that has happened.
Yeah, I think it's important to temper the enthusiasm and let people know that, this is not a commercial product. We're not anywhere near that stage yet. And there's still wrinkles to iron out, but the proof of principle has already been shown. It definitely does what it says on the tin. It's very, very adhesive to bone. It's very adhesive to metal. It'll stick the two together. It'll stick bone to bone together, and it'll do it in a wet bleeding environment, etc., etc. So all of that's now proven. Now we've got to make it so that it's highly predictable, so that we get the same outcome time after time, and we don't find ourselves in a situation where 30% of the time it doesn't work.
Right.
And that's where we're at.
Amazing.
Well, I think that as we expected, we would have a good time with this conversation. Definitely have. I think if you've not read the research, now's the time. You're probably frantically searching PubMed for information about this, because it is exciting. It's exciting when we get to see the progress of what we can do.
I tell you what's also exciting, actually, for the dental profession, is to have got there before the orthopedic profession. That we are always now going to be the profession that brought this into PubMed.
Now that's pretty special.
It's pretty crazy to think.
And for me to be one of those authors, it's a big deal for me.
Yeah.
At least that's how I see it.
I think it's a big deal. Congratulations.
And, we're looking forward to
hearing
that.
more about it and studying more about it. It has such a cool commercial name. Can we say that?
Yeah, I think we can say it.
Yeah.
We can say it.
This isn't the BBC, is it?
No, we're not. You're not Clarkson, thank God, right?
But if you know Superman, you know about kryptonite and how it hurt Superman.
Yeah.
This is not kryptonite. This is tetranite.
I don't know that you could have finished the show any better than with that comment there. So, Dr. Norton, thanks for being with us once again.
Maybe you should call me Clark Kent.
Any day.
My son is Clark.
Oh, perfect. That's even more perfect.
Even better.
Well, if you've listened to this and hopefully you've enjoyed what, we'd like you to just share what you've learned today. Share this video, give it your likes, subscribe as well. Check out osteo.org and the AO's social media as well. We're going to continue to bring you great content from the AO 2024. So for Mike Norton, I'm John Rogers and Wes Mullins, and we are the Dental Guys.